Hello everyone. I am delighted to participate in CVPR here. My name is Su Hyaming, currently studying at ZN University of Electronics Science and Technology. My purpose today is to briefly introduce our recent work. This is a deep fair multi-view clustering task. I will explain it to you in 6 aspects. With the development of data acquisition techniques, more and more multi-visual data are being acquired. Multi-visual data refers to different representations of the same object. For example, the same picture can have different feature representations. Research has shown that multi-visual-based learning methods are more effective than using only single vision. Multi-visual clustering is a basic multi-visual learning method. Its goal is to find the consistent structure in multi-visual data and in this way, to classify the multi-visual data into different groups. Existing multi-view clustering ignores sensitive attributes such as gender, race, age, etc., introducing additional bias and leading to unfair results. Ping's multi-view clustering aims to address these challenges. It focuses on creating clusters that are not only based on the underlying data schema but also consider fairness. This means ensuring that the clustering process is not distorted by missing data and that samples are fairly distributed across clusters. Unfair clustering leads to inaccurate groupings, while fair clustering attempts to balance the data distribution. The ultimate goal is optimal fair clustering, which achieves a harmonious balance between fairness and accuracy, making it more reliable in practice. Existing methods are constraint-based optimization, representation-based learning, and objective function tuning. However, these methods force the sensitive attributes in each cluster to be equal in order to achieve the desired fairness, which may be inconsistent with their true cluster distribution, leading to a trade-off between cluster performance and fairness assurance. Furthermore, these methods extract features via CNN or MLP, which cannot effectively approximate complex continuous functions of multiple variables. To address these challenges, we introduced the Attention Kolmogorov-Arnold network, KN, which has gained traction for its ability to model complex nonlinear functions. Existing methods often overlook the dynamic interaction between multi-view features and sensitive attributes, focusing solely on linear transformations or simple attention mechanisms. Inspired by KN's capacity to decompose multivariate functions into learnable univariate components, we propose fusing it with a hybrid attention mechanism to dynamically prioritize clustering relevant features. Let's start with the overall architecture. DFIM-CA KN consists of 3 core modules: the Attention KN Learning Module, the View Contrastive Module, and the Fair Clustering Module. The entire process is end-to-end, allowing the model to automatically extract effective features from raw multi-view data and ultimately output fair and consistent clustering results. At the input stage, we design a dedicated encoder-decoder pair for each view. The encoder integrates an enhanced attention mechanism and a KN network. The attention mechanism here is not just the traditional SE attention, but also incorporates multi-head double attention, enabling the model to capture both global and local feature information. The KN network further enhances the nonlinear representation of features through kernel interpolation. The encoder's output is then further abstracted by a multi-layer perceptron, resulting in a high-level feature representation for each view. The decoder's role is to reconstruct the original input from the high-level features, enabling self-supervised learning. By minimizing the reconstruction loss, we ensure that the features extracted by the encoder are both discriminative and informative, thus improving robustness. Next, the high-level features from each view are fed into a label learning module, essentially a fully connected network with softmax, to generate the probability distribution over clusters for each sample. Here, we introduce a view contrastive loss. Specifically, we want the clustering probability distributions for the same sample across different views to be as consistent as possible. This explicit constraint helps maintain semantic consistency across views and prevents noise or bias from any single view from dominating the clustering outcome. After obtaining the features from all views, we use an adaptive fusion mechanism to integrate them into a unified embedding. The fusion weights are learnable, allowing the model to automatically adjust the importance of each view. The fused features are then passed to the Fair Clustering Module. We use a soft clustering method based on the student's t-distribution to assign cluster probabilities to each sample. More importantly, we introduce a distribution alignment constraint during clustering to ensure that the cluster distributions are as consistent as possible across different groups or views, thus achieving fairness and preventing any single view or group from dominating the clustering. Next, I will give a detailed introduction to the objective function design of the DFIM-CAN model. The optimization objective of the entire model consists of three loss terms: reconstruction loss, contrastive loss, and fairness loss. Each loss corresponds to a core goal in the model design, and together they ensure the robustness, consistency, and fairness of the model. First, let's look at the reconstruction loss, denoted as L_R. As shown in Formula 1, the essence of reconstruction loss is to minimize the Euclidean distance between the input sample and its reconstruction for each view. Specifically, for each view V and each sample I, we compute the squared difference between the original input x_I_V and the decoder output x_I_V, then sum over all views and samples. This ensures that the encoder and decoder can effectively capture and restore the information of the original data, thus improving the robustness and expressiveness of the features. In the code, this loss is implemented as the mean squared error, MSE, between the input and reconstruction for each view. The second part is the contrastive loss, denoted as L_C, which is further divided into two terms, L_C1 and L_C2. L_C1 is mainly used to constrain the clustering distributions of the same sample across different views to be as consistent as possible. Specifically, for all pairs of views U, V, we compute the distribution distance L, U, V between them and average over all different view pairs. This explicitly encourages the model to produce consistent clustering probability distributions for the same sample across different views, thus enhancing semantic consistency and multi-view clustering. L_C2 is the intra-view clustering entropy loss. It computes the cross-entropy of the clustering probability distribution R_J_V for each view, encouraging the model to output more confident and concentrated clustering probabilities, and avoiding overly ambiguous clustering results. The total contrastive loss L_C is the sum of these two terms. In the code, this loss is implemented by comparing the label probability distributions and adding entropy regularization. The third part is the fairness loss, denoted as L_F. The core idea here is to ensure fairness in the clustering results through distribution alignment. Specifically, we first use the student's t-distribution to compute the similarity between each sample and each cluster center, obtaining the soft assignment probability Q_ij. Then, we normalize to get P_ij, which represents the probability of each sample belonging to each cluster. The fairness loss is calculated as the KL divergence between the clustering distributions P_ij and Q_ij for different groups G, encouraging the clustering distributions to be as consistent as possible across groups, thus suppressing bias in the clustering results. In the code, this corresponds to the clustering layer and distribution alignment implementation. We used 4 data sets with sensitive attributes for our tests, refer to table as shown in Table 2. Our method outperforms all baselines on all 4 datasets in both clustering accuracy, NMI, and fairness, BL. Especially on datasets like Zuffer and banking market, we achieve the highest scores, demonstrating both superior clustering and fairness. Table 4 presents the ablation study. Removing the fairness module leads to a clear drop in BL, showing its importance for fairness. Removing the semantic contrastive module also reduces both NMI and BL, indicating its contribution to both clustering quality and fairness. Only the full model, with all 3 losses, achieves the best results in both metrics. First, Figure 2 uses TSNE to visualize sensitive feature distributions in the bank marketing and Zuffer datasets. On the left, raw features show clear separation between sensitive groups. On the right, after applying our fairness module, the groups are more mixed, indicating that our model effectively reduces the impact of sensitive attributes and improves fairness. Figure 3 shows the NMI and BL results of our method under different combinations of hyperparameters lambda and beta. The model consistently achieves high accuracy and fairness across parameter settings, demonstrating strong robustness to hyperparameter choices. Finally, Figure 4 presents the convergence curves. Both pre-training and contrastive losses decrease rapidly and stabilize, indicating that our model trains efficiently and converges well on all datasets. Our proposed fair multi-view clustering method based on the K-and attention mechanism effectively overcomes the limitations of previous approaches regarding the distribution of sensitive attributes. By leveraging contrastive learning, we achieve both consistent and distinctive representations across multiple views, leading to a deeper understanding of the data. The introduction of a fair loss function ensures that clustering results are not only accurate, but also fair with respect to sensitive attributes. Extensive experiments demonstrate significant improvements across various datasets, establishing our method as a robust and practical solution for fair multi-view clustering in sensitive scenarios. And that concludes my presentation. If you are interested in it, you may consider perusing our research paper or reaching out to us for further discussion. Thank you for your time and attention.